Welcome to our lesson on Raoult's law. Today, we'll explore this important principle in chemistry that helps us understand the behavior of solutions, particularly how the addition of a solute affects the vapor pressure of a solvent. Before we dive into Raoult's law, let's understand what vapor pressure is. Vapor pressure is the pressure exerted by a vapor in equilibrium with its liquid phase at a given temperature. It's a measure of the tendency of molecules to escape from the liquid state. In a closed container, molecules constantly escape from the liquid surface to become vapor, while some vapor molecules return to the liquid. When these rates become equal, we have a dynamic equilibrium, and the pressure exerted by the vapor at this point is the vapor pressure. Now, let's understand Raoult's law. Raoult's law states that the partial vapor pressure of a component in a solution is equal to the vapor pressure of the pure component multiplied by its mole fraction in the solution. Mathematically, we write this as Pa equals Xa times Pa degree, where Pa is the partial vapor pressure of component A in the solution, Xa is the mole fraction of component A in the solution, and Pa degree is the vapor pressure of pure component A at the same temperature. First, let's discuss ideal solutions. An ideal solution is one where the interactions between molecules of different components are the same as the interactions between molecules of the same component. In simpler terms, in an ideal solution, each molecule behaves as if it were surrounded by molecules identical to itself. For an ideal solution of two volatile liquids, A and B, the total vapor pressure follows Raoult's law for both components. The total vapor pressure, P total, is the sum of the partial vapor pressures. P total equals Pa plus Pb in this graph. Xa represents the mole fraction of component A, and Xb equals 1 minus Xa. When Xa equals 0, we have pure B, and the total vapor pressure equals Pb degree. As Xa increases, the partial pressure of A increases linearly according to Raoult's law, while the partial pressure of B decreases linearly. When Xa equals 1, we have pure A, and the total vapor pressure equals Pa degree. Now, let's look at non-ideal solutions. In reality, most solutions don't behave ideally because the interactions between different molecules are not the same as between identical molecules. Non-ideal solutions deviate from Raoult's law. These deviations can be either positive or negative. Positive deviation occurs when the total vapor pressure is greater than what Raoult's law predicts. This happens when the interactions between the different components are weaker than the interactions between molecules of the same component. Examples include mixtures of ethanol and water, acetone and carbon disulfide. Negative deviation occurs when the total vapor pressure is less than what Raoult's law predicts. This happens when the interactions between the different components are stronger than the interactions between molecules of the same component. Examples include mixtures of chloroform and acetone, water and nitric acid. Let's solve an example problem involving Raoult's law. The vapor pressure of pure benzene at 25 degrees Celsius is 95.1 mmHg. Calculate the vapor pressure of a solution prepared by dissolving 7.8 grams of a non-volatile solute in 78.0 grams of benzene at the same temperature. To solve this problem, we need to find the mole fraction of benzene in the solution and then apply Raoult's law. Step 1. Let's calculate the number of moles of benzene. Given mass equals 78.0 grams, and the molar mass of benzene is 78.11 grams per mole. Number of moles of benzene equals 78.0 grams divided by 78.11 grams per mole, which equals 0.999 moles. Step 2. Calculate the number of moles of solute. Let's assume the molar mass of the solute is 156 grams per mole. Number of moles of solute equals 7.8 grams divided by 156 grams per mole, which equals 0.05 moles. Step 3. Calculate the mole fraction of benzene. X benzene equals moles of benzene divided by total moles. X benzene equals 0.999 divided by 0.999 plus 0.05. X benzene equals 0.95 to step 4. Apply Raoult's law to calculate the vapor pressure of the solution. P solution equals X benzene times P benzene degree. P solution equals 0.952 times 95.1 mmHg. P solution equals 90.5 mmHg. Raoult's law has several important applications in chemistry. First, it helps us understand colligative properties, which depend on the concentration of solute particles rather than their identity. These include vapor pressure lowering, boiling point elevation, freezing point depression, and osmotic pressure. Second, Raoult's law is fundamental to distillation processes, which are used to separate liquid mixtures based on differences in their volatilities. Third, Raoult's law helps explain the formation of azeotropes, mixtures that boil at a constant temperature and cannot be separated by simple distillation. Let's summarize what we've learned about Raoult's law. Raoult's law relates the vapor pressure of a component in a solution to its mole fraction and the vapor pressure of the pure component. Ideal solutions follow Raoult's law exactly, while non-ideal solutions show positive or negative deviations. Positive deviation occurs when the total vapor pressure is higher than predicted, indicating weaker interactions between different molecules. Negative deviation occurs when the total vapor pressure is lower than predicted, indicating stronger interactions between different molecules. Raoult's law is fundamental to understanding colligative properties, distillation processes, and the formation of azeotropes. Thank you for watching our lesson on Raoult's law. I hope you now have a better understanding of this important principle in chemistry.